Another tool we use when we're counting is the multiplication principle. The multiplication principle says that if there are m ways to complete task 1, and n ways to complete task 2, then the number of ways to complete both tasks is m times n. So for example, let's ask how many alphanumeric codes are there? If the first symbol is a letter somewhere between A and Z, and the second symbol is a number 0 through 9. The answer is, so we've got two things to choose. Our first task is to choose a letter. So there's 26 ways to choose the letter. And for the second symbol, that's going to be a number, and there's 10 ways to choose the number. So 26 times 10 is 260. And then a related question, what if both of them can be alphanumeric? So we could have a letter or a number in the first digit and a letter or a number in the second digit. And the answer is then we'll have 36 choices for the first and 36 choices for the second. So 36 times 36, whatever that is. And now let's make this a little bit harder. And let's say, what if both symbols can be a letter or a number, but they can't be the same? So we don't allow a repeated symbol. I can see two ways to look at this problem. First way is, well, there's 36 times 36 total codes minus 36 bad ones. Minus AA, BB, CC, all the codes that have the same letter repeated. So that's 36 times 36 minus 36, and we can factor a 36 out of this pretty easily. 36 times 36 minus 1, which is 36 times 35. Let's not bother multiplying that out. And there's a second way to look at this, which is just as easy. Kind of like this. So the second way is, well, think about these two tasks to complete. The first task is to put something here. So there's 36 symbols that we could put there. And then for our second task, we're going to put something in the second position which is different from what we put in the first position. If it has to be different from what we put in the first position, then there's 35 symbols left. All the symbols minus the one that we used already. So 35 other symbols not equal to the first. So 36 times 35. We'll get the same answer, which is good. It's the right answer. 36 times 35 codes that are alphanumeric if the two digits can't be the same. All right, now multiplication extends to multiplying several numbers at a time. And maybe we have more than two tasks. Maybe we have k tasks to complete. So if we want to count the number of ways to complete k tasks, I'll just say the number of ways to complete k tasks is number of ways to complete the first times the number of ways to complete the second times the number of ways to complete the third, etc., times the number of ways to complete the kth. So we just perform all those tasks and count the number of ways to do it. So, for example, we can talk about code words that are more than 2 digits long. We can ask how many binary words are there of length 7? So these are words A1, A2, A3, etc. up to A7, where each digit is 0 or 1. So the answer is, let's think about these 7 digits. The first one is 0 or 1. And the second one is 2, etc. Every single one of these is 0, 1. So we have 2 choices, 2 choices, 2 choices, 2 choices. And we say that 7 times. So I guess there's 2 to the 7th binary words of length 7. Because our first task is to fill the first place. There's 2 ways to do that. And then our second task is to fill the second place. And there's 2 ways to do that, etc. And we have 7 tasks, 7 places to fill with a 0 or 1. So 2 to the 7th. And what if the words are, instead of binary, what if they're alphabetic codes? So A through Z. Well, there's 26 letters, so 26 to the 7th, whatever that is. In this class, a lot of times, we're not going to multiply out numbers. If you write 26 to the 7th, I know exactly what you're thinking. 26 times 26 times 26, 7 times. If you were to plug that into a calculator and give me whatever number it turns out to be, it'd be some huge number I wouldn't recognize. Nobody would recognize it. Nobody has 26 to the 7th memorized. So I think the simplest way, if we're going to simplify and express everything as simply as possible, 26 to the 7th is simpler than whatever you would get if you plug that into a calculator. And what about alphanumeric codes? So alphanumeric codes, A through Z, or 0 through 9. Well, now we've got 36 characters to put in each one of the positions, so now it's 36 to the 7th. Again, please don't type that into a calculator and figure out the expansion of it in decimal. I'd rather see 36 to the 7th than whatever that number turns out to be. Alright, now let's throw in the variation where we can't reuse a letter. So what we choose second has to be different from what we choose first, and then after that has to be different than the first two things we've chosen. So how many, let's say, alphanumeric codes of length 7 have no repeated letters? Now we solved a similar problem two ways, but I think subtraction rule is going to be a little hard to apply here, because we would have to know how many alphanumeric codes do have repeated letters, and that's not very easy to count. For 2-letter words it's easy because you just count the number of letters you have. But for 7-letter words, they could have a letter repeated 7 times or 6 times or 5 times. There could be 2 different letters repeated. There's lots of possibilities. That's hard to count. But so I think the other way that we counted is easier. So we've got 2, 3, 4, 5, 6, 7. We've got 36 choices for the first letter. And then once we used one of the letters, we only have 35 choices for the next letter. And then once we use 2 letters, we only have 34 choices for the next letter. And every task that we complete here, which is choosing a letter, can be done in 1 fewer ways than the task before it, because every time we complete a task, we have 1 less letter to work with than we had before. So 33, 32, 31, and finally 30 letters for that last position. So the answer is the product of these numbers, whatever that is. Again, please don't type it into the calculator and give me some huge number that I'm not going to recognize. Maybe there is one more expression for this, which is just as simple as what I wrote, or maybe even simpler. Because we can see this is the beginning of 36 factorial. 36 factorial is 36 times 35 times all the numbers all the way down to 1. So we could write this as 36 factorial divided by 29 factorial, because 29 factorial is all the numbers that we're not including here, 29 down to 1. Now a special case of this problem is how many rearrangements of n letters are there? So that's the question. The answer is n factorial. Using the same reasoning as here, because we've got n choices for what letter we're going to put first in our rearrangement, and then n minus 1 letters for what we put second, and then n minus 2 letters for what we put third, etc., all the way down to 2 times 1. So we're going to multiply all the numbers from n down to 1, all the integers. So there's n factorial. These are called permutations. Those are permutations of n letters, different ways to write them all down, every letter exactly once. Ways to rearrange them into a line. And then the more general problem, which is what we just solved using the number 36 and 7, we could ask how many 7-letter repetition-free, let me say k letters so we have a general formula here. How many k-letter repetition-free words can we make with n letters? And the answer we get, well, by considering the same picture here. We've got k blanks. And we've got n choices for the first blank, and then n minus 1 choices for the second blank because we used one of those n letters and we're not allowing repetition. N minus 2 letters for that third blank. And then let's see, how many do we have for the last one, the kth blank? If the first blank has n minus 0 choices, and the second blank has n minus 1, and the third blank has n minus 2, I guess what we're subtracting is off by 1 from the number of the blank we're looking at. So the kth blank has n minus k minus 1 possibilities, or n minus k plus 1. So we could multiply all these numbers together and say that's our answer, and that's one way to express it. That's not bad. N times n minus 1 times n minus 2, etc., down to n minus k plus 1. Or we could use the fact that this is the beginning of factorial. It doesn't necessarily go all the way down to 1. And n minus k factorial describes all the numbers that we're leaving off here. The next number after this one would be n minus k. So n minus k minus 1. The product of all those numbers from n minus k down to 1 is n minus k factorial. Now if we wanted to make this into a probability problem, we could say n factorial over n minus k factorial pieces of paper are placed into a hat. One for each of the k-letter repetition-free words that we can make with n letters. I'll just say one for each of the words above. And then we could ask, what's the probability that if we choose one at random that we get any particular word? what's the probability that a randomly chosen word is, let's say, the decreasing word that starts with, well, let's say the increasing word. 1, 2, 3, etc. up to K. So that's one K letter word with no repetitions that uses letters 1 through N. Not all of them, obviously. We can't use all of them if K is less than N. And the answer is, well, it's 1 over the number of pieces of paper in that hat. So 1 over n factorial over n minus k factorial. And 1 over a fraction is the reciprocal of that fraction, so I guess we could also say n minus k factorial over n factorial. All right, now let me do a related problem. It's maybe a little bit more complicated. So let's ask how many numbers 1 through 1,000 are written with 3 distinct digits. So no numbers with repeated digits. No 311, no 222. So how many of those numbers have 3 different digits? Well, the digits are going to be 0 through 9. So there's 10 choices for the first one, times 9 choices for the second one, times 8 choices for the third. That's almost the right answer, but if you think about it, we don't want to count numbers like 0 to 1, because 21 isn't really written with the 0 first. We just write it to 1. And we don't want to count 47 either, 0, 4, 7, because it's not really written with the 0 first. So we have to subtract off all the numbers that have 3 different digits and start with a 0. We don't want to count those. So how many of these are there? So the number of these is, well, let's draw them and see if we can use the picture to decide how many there are. So the first digit is 0. And then the second digit is something 1 through 9. And then the third digit, I guess, has 8 choices, because it's also, oh no, that could be 0. So that could be anything except for these 9, or it could be 0. Sorry, anything except for the 1 digit that we put here, and it could also be 0. So let's, I'm sorry, it can't be 0, because we're starting with 3-digit numbers that have 3 different digits. So we wouldn't have 070 or anything like that. We're only subtracting off the numbers having 3 different digits where the first digit is 0. So this is 1 through 9, and this has 8 choices. Anything except for what we put here. And it's certainly not going to be 0 because we're subtracting from a set that didn't have 2 zeros in the first place. So there's 9 choices for here, 8 choices for there, so 9 times 8. So the total good numbers total of good numbers is 10 times 9 times 8 minus 9 times 8. And I guess we can factor out 9 times 8, and maybe the simplest way to write this is 9 times 9 times 8, or 9 squared times 8. I think all of these expressions are reasonably simple. 81 times 8 wouldn't be terrible, but if you multiplied 81 times 8, I think that would look a little bit more confusing and would not be as simple. The end.